good. Thank you.
Yep.
Yeah, so a geometric sequence is a pattern where we multiply every time. So in other words, to get that pattern, we're going to repeatedly multiply. Okay? What does it mean when you use an exponent? What does an exponent mean? Yeah, multiply by itself, right? Repeated multiplication, right? So if we have, like 3 to the 4th, right? That means 3 times 3 times 3 times 3, okay? And so for our patterns, since we're repeatedly multiplying by the same number over and over again, right? Then it makes sense that we're going to use exponents. And in fact, when we saw our formulas yesterday for a geometric sequence, okay, we had an exponent, right? Our variable was in an exponent because we were repeatedly multiplying by that common ratio. Okay, well, we're also going to be talking about exponential functions. Okay, this is an exponential function. Okay, what gives it away that this function's exponential? Well, where's our variable? Where's our x variable? In the exponent, right? Okay, that's what makes this function exponential, right? When we talk about quadratic functions, what do we see in an exponent? In the place of the exponent. So for like a quadratic function, it's quadratic because there is what number in the exponent? A 2. It's a degree 2 or power of 2, right? And a linear function is linear if we see what for our exponent? A 1 or nothing, right? Because a 1 is implied if you don't write anything, okay? So that's kind of like, what we're looking at here, all right? So let me just kind of break this down a little bit. So the y value here, okay, so how do I want to do this? Let's do it this way, okay? So this is our normal y value, okay? We'll say it's the dependent variable, right, if you remember that. Okay. The a, excuse me, you could think of that as like our, in the context, it means the starting or initial amount, okay, if there's a context, okay? You could also think of this, or you could think of this, it's our y-intercept, okay? Okay, so y equals a times b dx. Y is just, of course, our y value, the dependent variable, right? We see y show up all the time, right, when we're trying to graph stuff. A, okay, it's like the starting or initial amount, or you can also think of it as the y-intercept of the graph. Okay, it's the y-intercept of the graph. Okay, and then b, okay, b is known as the growth / decay factor. Okay. Now, how could something be both growth or decay? Well, it can't. You can't grow and decay with the same value simultaneously. But it's going to change depending on what the number of what b's value is. For certain values of b, we'll call it a growth factor because it's going to make our function grow and grow and grow and grow, right? But for other values of b, it's going to make our function get smaller and smaller and smaller and smaller, and so we're going to call that a decay, okay, a decay factor. Okay? Will I be posting this on Classroom? Yeah, of course. The video and stuff, yes, exactly. Am I going too fast or something? Or you're good? Yes? No? Yes? Okay. I can slow down a little bit here. Okay. Another little note here, and we'll look more at this later. B, okay, for later when we're talking about like context of problems, okay, B is actually made up of a number plus, or 1 plus another number, R. Okay, now I know this is going to be confusing. This R here, okay, so then this is our, again, this is our growth factor. Okay, R though is not a growth factor, it is our rate. Okay, so we're using the word R for the growth or decay rate. Okay, so you'll see here what I'm talking about. Okay, so eventually we're going to get to the point where B, in some situations, B will be, well, it's always going to be referred to as our growth or decay factor. But sometimes B will also be referred, we'll use B to find this growth or decay rate as well. And the rate typically is a percent Okay, that's why. So it's a percent growth or percent decay. Okay. Okay. What I mean by that is something like you could have a situation where you're growing 10% each minute or something like that. Okay, like a population of bacteria. Okay, they grow 10% per minute. So we're going to have a growth rate of 10%. The rate would be 10%, but then our B will be something else. And again, we'll get more into that when we get more into context and stuff like that. But I just want to introduce the idea here. Okay? So these are all the pieces of our exponential function. Okay? So in some senses, it's easier than quadratic, right? There's not so many pieces. There's not like A, B, and C, right? There's fewer pieces going on here, right? But each one of these pieces are kind of packed with meaning. And of course, then there's our x, okay? And our x is our independent variable, okay? Which is no different, okay? X is going to typically represent time. Okay, x is going to typically represent time. Okay, time. Okay, especially in our word problems, we're going to be using it as time. Okay, so any questions so far? No? All right, so then let's skip down here. Okay, so, oh, sorry, I see some people still right now. I want to move on too fast there. My bad. Okay. I'll just read the special note here. So the special note underneath here, it says, any quantity that grows or decays by a fixed percent, that means a percent, a unchanging percent, okay, at regular intervals is said to have exponential growth or exponential decay. Okay, so that's where that R comes in. And again, we'll see more of that showing up here in a little bit. We don't have to worry about it too much right now, but we will, as we go, we'll see more of that show up. So let's just try and focus on graphing right now. Okay, let's take a look at this. Okay, so from this information, okay, and what we just learned up here, right, what is our A in this situation? And number one, what's our A? 1, right? Yeah, A is 1. Okay, very good. Okay. And what is our B? 2. Okay, A is 1, B is 2. Now we go up here, right, we can refer back to this. Okay, if A is 1, A then, that's our starting or initial amount, or it's our y-intercept. So we know that our y-intercept then is 1. So I can put a point on the y-axis at 1, and I know there's a point right there. Okay, I got the point, 0, 1. It's my y-intercept. Okay, so I can put a point there. Okay. Now, of course, is that enough to graph our function here? No. No. So what can we do to maybe graph this? How have we graphed things in the past? What have we used? So, Olivia? Yeah, we can make a table and use our graphing calculators. Exactly right. So let's go ahead and start with that y-intercept. I'll make a little xy chart here. And if you have your graphing calculators, I suggest you get those out. I'll put that, I'll put the point, the 0, 1, my y-intercept in the middle again. And let's just get a few points before it and a few points after. So for 0, I'll go -1, -2, and then after 0, I'll go 1 and 2. And if we need to get more points, we'll do that. Okay, but again, I'm going to put that y-intercept in the middle there. All right, and so let's go type this into our calculators. Okay, let's see if I can get this to show up. There we go. All right, in my calculator, okay, I'm going to type in 1 parenthesis 2 to the x. Okay, just like you see it, use parentheses, please. Okay, do use parentheses and things. All right. And then now that I have it graphed, what should I go to kind of help me fill out my table here? What do I need to press now to help me fill out my table? So, Sky? Yeah, second graph. Okay, and there's my table. All right, so let's see here. I have -1, and that is at 0.5. So I'll go ahead and fill that in. So -1 gives me 0.5. Okay, -2 gives me 0.25. Okay, 1 gives me 2, and 2 gives me 4. Okay, let's keep going here and see what happens. So 3, well, just look at our pattern here. What do you think 3 is going to give us? We went from 1 to 2 to 4, then to 8. Remember, guys, these are exponential. We should see a geometric pattern here. We should be multiplying by 2 every time. Okay? So I'm going to graph these points now. So I think that's the most we can fit. No, we can fit one more. 4, what will be the next one? 1, 2, 4, 8. 16. Yep. So let's plot all these points then. Okay. So -1 and then 0.5. So it's like right there. -2 and 0.25. So even lower. Okay. Let's go to 1, 2, 2, 4, 3, 8, and 4, 16. Okay? Plot those points. Now, when we were talking about geometric sequences, okay, and we graphed a geometric sequence, we did not connect the dots, right? That made it discrete. In this situation, should we connect the dots? Could our x values be something other than just like whole numbers? The answer is they could be, yes. We actually can put in fractions in for x here. If you don't believe me, well, let's take a look at the graph here. You can see the calculator, when I graph it on the calculator, it connects the dots, right? It makes it smooth. So that means this graph is continuous. It is a continuous graph. So we're going to connect the dots here. Okay, I'm going to draw an arrow because it looks like it keeps going. I'm going to draw an arrow this way too. Oof, I did not do a very good job here, I feel like. -1.5. Oh, that's why. I did too low. That's where I should have put my point. I put my points in the wrong spot. Sorry, folks. They should be right there. Okay. Now, when I go to the right here, you can see we're just going to keep going up and up and up and up. Bless you. Bless you. But then as I go to the left, as my x values go to the left here, look at my y values. What's happening as I go further negative? What's happening to my y values? So, yeah, John? We're dividing by 2, right? So 1 divided by 2 is 0.5, divided by 2 is 0.25, divided by 2 will keep going. If I keep dividing by 2, will these ever be negative?
No. I don't know.
Why not?
Because it just keeps on going to this one.
I have a positive number and I'm dividing by 2, a positive 2. It's always going to stay positive. So in other words, this line should never cross over to the negatives. In this case, right? We'll never cross over into the negatives because I'm just going to keep cutting in half, cutting in half, cutting in half, and it's going to stay above the x-axis. Okay? Yeah. How might we describe the domain of this graph? What's the domain here? What's the farthest left it looks like this graph goes? Go ahead, Alex. Okay, the farthest left it looks like it goes is negative infinity. How about the farthest right it looks like it's going to go? Positive infinity, yeah. It's going to keep going to the right. It's just it's going up so much that it's hard to see. Yep. Okay. Here's a bit of a trickier question. What's the range then? What do you think the lowest y value is going to be here? We know it doesn't go negative, so what's the lowest y value we're going to have? 0. But it will never reach 0 because it's just going to be keep cutting half and half and half. So it's always going to have a little bit more than 0 because we're just having it. So we're going to put 0 but exclude the 0. Up to, and now what's the highest y value this graph is going to have? Infinity. Okay? Very good. All right. You guys go ahead. Try number 2. I'll help you get started a little bit here. All right. What's our A for number 2? 2. What's our B? 3. Okay. And so our y-intercept is what number? 2. So I'm going to put a point here at 2. Okay. And then I'm going to fill out a little chart. And I'm going to put that point 0, 2, the y-intercept in the middle. And I'll do some points before and I'll do some points after. So we'll do -1, -2, 1, 2. Okay. So go ahead, fill in the rest of the chart there. Okay. Use your graphing calculators if you want to, or just do it paper and pencil. Okay. But go ahead, folks. Try number 2. Fill that one out, please. I'll do it as well. Already? Very good. So go ahead, graph this one, please. And then if you want to, go ahead and answer the question at the bottom. Think about how you might want to answer the question at the bottom. Once you graph the points and connect the dots, okay, think about how you might answer that question at the bottom. What might you say about these two graphs? What do you notice about how they're similar, I'll say. So you want to use the caret button, and then x. And that puts it to the x power. Okay, good question. Sorry, I didn't specify that. All right. Fill it out there. Use your graphing calculator. Do you have a graphing calculator? Okay. Why don't you get that out? It'll help you, I promise. All right. That video will not help you. It distracts. Question, Lillian? You're good? Looks good. The only thing I do have an extra one. The only thing I'll specify here, don't let it go below the x-axis. If it's going to stay positive, because we're just going to keep dividing by 3 every time, and it's never going to make that negative, so it's going to flatten out, and it won't actually cross the x-axis. So just be careful with that. That's it. Okay. Do you mean one, Mr. Steer? Is that what it is? Oh, you need one, Ethan? Sorry. Thank you. You're welcome. Thank you. You're welcome. Okay, try, man. Let's try these out, okay? It's not going to help you, whatever you're looking at right there. Okay. Well, number 2. Do you have your graphing calculator handy? Okay, you want to get that out. Okay, we'll graph it here. Yeah, you set it up correctly. So now what I suggest you do is press second graph, and then you can go to your table and help you fill out your table easy that way. All right, Lexi, why don't you get your graphing calculator out so you can check along. Yes. Do you need a graphing calculator? You got it. Yeah, type it in. See if you can fill it out. Oh, very fancy. Fortune teller. That's not why you're inside. Most charges. That's good. That's good. Are you doing okay?
I keep on getting 6s.
6s. Yes, I think. Let's see how you typed it in.
Not right.
I see 2 times 3, but what are you missing?
The x.
Yes, at the end, the caret. You need to use the caret. You need 2 to x. 2 to the x. Now, and then, sorry, what? Write that down.
I get this.
And then go to second graph, Brady. Second graph, and that'll get you your table to help you fill it out.
This is infinity.
All right, 30 more seconds here, folks. What? 30 more seconds here, folks, okay? Okay.
Just start at like 0. You want me to go out this way too? That's one. Like -2 would be like 2. I don't like this one. This is
Okay. Here's what your graph should look like. Okay. For those of you that just are tuning in now, okay, don't worry. We're going to have a few more to look at here on the back, so don't worry about that. Okay, but I ask that you do follow along for these next 2. Okay, just make sure you get it down. All right, you know how to do it. This is super important. It doesn't get easier from here. All right, so you want to make sure you have the solid You want to make sure you have a solid foundation for us to build on for later. Okay. Right. When you build a building, you don't want to like leave a whole bunch of bricks out and stuff like that, or else the building's going to fall over. We want a solid foundation to build on for later. Okay, that's what we're doing right now. All right, so what do you notice about both these? Actually, let's do the domain here just because we can. Okay, so the domain. Okay, what's the domain for this graph going to be?
of negative infinity and positive infinity.
Negative infinity, positive infinity. You're right. And then the range. What's the lowest y value we're going to see here? 0, and it's not going to reach 0. Okay, so we'll exclude it, and then it goes up to infinity. Okay, so what do you notice about both these graphs? What kind of behavior do both of these graphs show? They are both what? Okay, positive, continuous. What about increasing, decreasing, or constant? They're both increasing. They are everywhere increasing. There's no place where this function is decreasing. There's no place where this function is decreasing. There's no place where this function is constant. There's no place where this function is constant. It is everywhere increasing. Even here, when it looks like it's flat, remember that we are slowly, very, very, very slowly decreasing as we go back this way. Well, sorry, it's really increasing from left to right. Okay, both are increasing from left to right there. Okay. Yeah, because of the direction that you go, depending which direction. But when we talk about increasing, decreasing, or constant, mathematically, we're always looking from left to right. So from left to right. From left to right, we're increasing. Okay. So, all right, flip it over.
All right.
Now let's take a look at this next one here.
I got it already.
All right. So again, what is our A in this case for number 3? A is 1. B is 1/2. Okay, so there's no C. Our A is our y-intercept. So at 1 we have our y-intercept. So put a point there. Make a little table. Okay, again, I'm going to put the 0, 1 y-intercept in there. And then I'll also do some points after, so like 1 and 2. And I'll do some points before, -1, -2. Okay. Please be careful how you type this in your calculator. We got to have a fraction in there, so make sure you type it in. So 1 parenthesis 1/2 to the x. Whoops, sorry. Wish I could just show everything at once, but no, this light's not quite working for me. Okay. So we graph it. Okay, there's the graph, and we go to the table. We'll see some other values here. So let's see. So I get -1, I get 2. At -2, I get 4. Okay, at 1, I get 0.5, and at 2, I get 0.25. Okay. So we'll plot these points to -1, 2, -2, 4, okay, and then 1.5, and then 2, 0.25. It's like right down there. Okay, can you see that okay? Okay, if you want to go, or you can use your graphing calculator to go earlier. So for example, -3 will give me 8, so I can even plot that point. -3, 8, that fits. And then also -4, 16 will fit as well. Okay, just like that. So -4, 16 will also fit, and -3, 8 will fit as well. And so then the other ones won't fit then. So we'll connect the dots again. So this is a continuous function. And it'll just get closer and closer to the x-axis, but never cross. Okay, we're not going to cross that x-axis. Okay. Question? Yes, I'll come take a look, or Mr. Seaver is going to come over. All right, there's number 3. Go ahead, try number 4, and then I want you to answer the question about what you notice about both graphs. So go ahead, try number 4. Okay, what's our A for number 4?
Oh, there's a point in here.
What's our A for number 4? 2. What's our B? 0.4. Okay, so it means our y-intercept is 2, so we know we have a y-intercept at 2. And again, we'll make a little table. Okay, put the y-intercept of 0, 2 in there. We'll go a couple points before, we'll go a couple points after. Okay. Go ahead, fill out the table, please. Use your calculator to do it. All right, use your calculator to help you. If you guys didn't do it on the front because you weren't paying attention, I want you to try it now, please. All right, please do it. And make sure you can do this. This is like foundational. We got to be able to build on something solid here. Oh.
It just keeps saying.
No, the plots are on, so if you arrow up and hit enter, there you go. Now that's your graph. Yeah. Classic. Okay, again, Once you got that fourth graph, what do you notice about both graphs? What behaviors do you see? Think about how we answered on the front. Answer similarly on the back here. Okay.
Why do you think you start at -3?
Because I want to give you some. I want to give you some more points. You're right. It doesn't fit, does it?
No.
So then, I chose poorly. Okay, so again, like 30 more seconds here. Okay, once you get those points plotted, please try and answer. What do you notice about both
I have
graphs
a question.
here?
I got 2 for 0. Is that a 3 or a 2? I got 2 for 0.
It should be 2 and
no,
then
for the 0 one. Is that
it should be 0, 2. 0, 2.
Oh, yeah, that's what I got.
a 2.
I thought it was a 3. Can I skip the first one?
Sorry?
Can I skip the first one because it's not, I can't plot it.
Which one can't you plot? Oh, -3. Yeah, of course you can. Yeah, of course. Of course. Yes. All right, here we go. Should have got something that looks like this. Wow. Poof. Okay. Now, I forgot to mention here for 3 and 4 what the domain is. What's the domain for both 3 and 4?
Are we taking a quiz?
-infinity to infinity. Are we taking a quiz right now? No, Brady, this is a lesson.
You said domain quiz.
Okay. Domain, okay, -infinity to infinity for both of these, right? We can go left and right as much as we want. Okay. What about the range for number 3? 0 to infinity again, okay? It starts at positive infinity, goes down to 0, but please don't put infinity to 0. Please don't put infinity to 0. You start at your lower y value first. The lowest y value we see is going to get closer and closer to 0 there, okay? And then it goes from 0, the highest y value we go to is infinity then, right? Please don't put infinity comma 0. That's not right. I know, Mr. Wee, we start at infinity and we go to 0. Why is it infinity comma 0? Because range goes from bottom to top, bottom to top. Okay? Same thing here. What's the lowest y value for number 4? 0. And what's the highest y value for number 4? Infinity. And beyond. All right. What do you notice about both graphs in this situation? They are both what? Okay? They're not negative. They're, so you have like I see what you're trying to describe here, but be careful. Negative means they're below the x-axis, right? All these y values are still positive, so it's still positive. It's still continuous, but is it increasing? Yes. So we're going to say this is decreasing. These are decreasing functions, right? So for both 1 and 2, we were positive and continuous, right? Positive and continuous. Positive above the x-axis and continuous. Positive above the x-axis and continuous. But we were increasing. Here, we were positive, right, above the x-axis and continuous, right? Nice smooth curve there. But we're decreasing. Now, let's compare equations 1 and 2 with equations 3 and 4. So here was 1. 1 was y equals 1 times 2 to the x. 2 was 2 times 3 to the x. Oops, I need to put a y there. Okay? Compare that with 3 and 4. 3 is 1 times 1/2 to the x. And 4 is y equals 2 times 0.4 to the x. No, I need you to stay for this real quick, and then I'll let you go. Okay. Unless you're gonna die of dehydration, but in which case you probably won't be able to walk there. So I have to give you emergency water or something. If you can just hang on for just a second, please, just for a few minutes. Thank you. So compare 1 and 2 with 3 and 4. 1 and 2, our exponential functions were increasing. 3 and 4, our exponential functions were decreasing. What do you think it is about 1 and 2 that makes them increase? What do you see about those that make them increase versus 3 and 4 that makes them decrease? Hannah T.
The b values are all more than, or for 1 and 2, they're more than 0.
Okay.
Or more than 1.
Ah, right. Okay, very good correction there. Okay, so for 1 and 2, b is greater than 1. Okay. What about in 3 and 4? What's special about those numbers? They are what? What about then 3 and 4? You're saying 1 and 2, b is greater than 1, but in 3 and 4, what happens? They're fractions. And specifically, they're fractions that are between, but I said in twice, 3 and 4, 0 is less than b is less than 1. In other words, the b values in 3 and 4, the fractions, right, are between 0 and 1. Because we've got to be careful. Just saying that they're a fraction, right? I could technically 2 is a fraction. 2 is a fraction is 2 over 1, right? 3 is a fraction. 3 is 3 over 1, right? But it's their value, okay? So b greater than 1, exponential. Well, what do you think we would call this? If b is greater than 1, we would call this exponential what? It gets bigger as we go, so exponential growth or decay? Growth, right? This is exponential growth. Okay? 3 and 4, where our b value is between 0 and 1, we would expect then exponential, what we call that? Exponential what? Decay. Okay, because our values are getting smaller, decaying, right? Decaying. Smaller and smaller values there. Okay? So, to summarize, when b is greater than 1, almost got away with it, all right? When b is greater than 1 and a is positive, okay, we also need to have a positive a value too. So when b is greater than 1 and a is positive, the graph will be increasing or growing. Okay? For exponential decay, when b is between 0 and 1, a, and also a is positive, a still needs to be positive here too. Okay? The graph will be decreasing or decaying. Okay? If a is negative, it kind of flips those relationships around. Okay? So we don't worry about that right now. All right? So there's the summary. Exponential growth versus exponential decay. Okay? Questions on any of that? Oh, take a picture. Sorry, am I going too fast for you, Brady?
Yes.
Sorry. Okay. Let me see here. I had some other things I wanted to say. I got to remember what I wanted to say. Oh, right. So there are some numbers that we're avoiding here. For example, right, so we're saying b is greater than 1. So this takes care of all, so if b is greater than 1, right, all the values greater than 1, right, we know that's exponential growth, right? For all the b values between 0 and 1, for all the b values between 0 and 1, so that takes care of those below 1 but above 0, right, that's exponential decay. What about if b is equal to 1? What are we going to have happen to our functions here if b is 1? What is our graph going to be if b is equal to 1 here?
Constant.
Constant. Why?
Because you're not multiplying the thing.
Well, we're still going to multiply, but what are we multiplying by every time?
By one.
Yeah, when you multiply by 1, what happens to the value of your thing?
It doesn't change.
It doesn't change, right? It's going to stay constant. So if I have b as 1 here, I'll have 1 to the x. I can do times 1, times 1, times 1, times 1, times 1, times 1, times 1. Nothing's going to change. It's always going to be equal to a. Okay? So if b is 1, do we even have an exponential function? No, because it's just 1 to the x, it's just 1, so it doesn't matter, it's always going to be 1, so it won't be even exponential. Okay? Notice we're also avoiding 0. What's going to happen if b is 0? It's going to be 0 to the x, and what happens when you multiply something by 0 repeatedly? What does it equal? 0. You get 0. So this will just become 0. You'll have y equals 0. This is a horizontal line through 0. Okay? Will that be exponential then, if b is 0? No. Okay? So if b is 1 or b is 0, you're not going to have an exponential function. So that's why we won't ever see that happen. Okay? B will never be just 1, or b will never be just 0, right? We have to have, you know, a number bigger than 1 or a number between 0 and 1 there. Okay? If b is negative, your calculator won't graph it. Okay? Because you get into all sorts of like funky situations if you have a negative b. If you try and make it negative, like I'll just change it here and make it negative 0.4x. I'll show you here. Your calculator won't graph it. See? It like was doing some work, but it didn't graph it. Okay? And oh, you can go to your table for it. All right. But anyway, yeah, it won't. Huh, now that's interesting that it actually does negative values. It shouldn't, but anyway. Okay. Those are imaginary. Anyway. My point is, b is going to have to be positive here. Okay? It's either going to be between 0 and 1 or greater than 1. And that gives you different functions there. All right. Questions on any of that? Yes, thank you for waiting, Brady. Appreciate it. All right, then. All right, yes. Yes. I got one more paper here. Thank you. So I got another paper here that's going to summarize some other important pieces. Okay, I got another paper here that's going to summarize some of these important pieces we just talked about. So I'm going to repeat some of the stuff we just talked about. Okay, but I just want to make sure that we, we got the main ideas down, because again, we're building a foundation here. These exponential functions. We want a solid foundation, no holes. Okay, we need something to build on. Okay, so thank you, sir. All right, so first one we're going to talk about exponential growth. So I'll zoom in on the top part there. Okay, so the general equation for an exponential growth function is y equals a times b to the x, where a has to be what? Positive. Okay. Now, okay. Now this is confusing here. Okay, if b is greater than 1, this shall be an exponential growth then. Okay. Okay, and like I mentioned earlier, b is going to be this thing we're also going to refer to this as, as the growth factor. Growth factor. In this case, because if b is greater than 1, we have exponential growth, so we're going to call b the growth factor. Okay? And again, r, we'll be calling that the growth rate. Okay, and again, how are b and r related? B is 1 plus r. Okay, and again, r is the growth rate, not common ratio. Okay, I know we're using R two different ways here, okay? So please forgive me, okay? In this case, the common ratio is actually B, right? The number that we're multiplying by every time for the pattern there, B is our common ratio there. Multiply by B every time. Okay, R though, for this situation, when we're talking about the common, the growth rate, okay? All right. And again, it makes sense for the growth rate, we're going to add the growth rate to 1 to get B then. All right. Then for the exponential decay, okay, for exponential decay, what do we know about A? A still has to be what? Positive. Okay. Yeah, and this is if 0 is less than B is less than 1. So we have to fix that one. Okay. So we're going to fix that. If 0 is less than B is less than 1, okay, that's an exponential decay. Okay. And so then when we had exponential growth, we referred to B as the growth factor. So for exponential decay, we should refer to B as the decay factor. Okay? And again, for R, it was growth rate. So for R in this situation, it's going to be the what? Decay rate. Okay? Now to find R in this situation, since it's a decay, it will be B equals 1 minus R. 1 minus R. Okay? And again, these will make a little bit more sense once we kind of get into the context of how we're going to be doing these. We're going to talk about like 10% growth. This means we're going to be adding 10% each time, which means plus your R, right? Because you're adding 10% each time. But then for a decay rate, we're going to subtract 10% each time. So that's why it's minus R. Okay, and again, growth rate. Okay, not common ratio. Okay, again, in this case, the common ratio would be B. That's the number you're multiplying by every time. B is the number you're multiplying by every time. Okay. So, what I would like you guys to do then, we're going to pause right there for this. I'm not going to finish these two, but if you flip onto the back, okay, if you flip onto the back, you'll see, okay, several problems here, okay, A through G, and for the directions are the same for A through G. Just identify it as an exponential growth or decay, and then for 1, and 2 here, you have to give examples for exponential growth and exponential decay, and this is what I would like you to work on. Okay, so this A through G should take you like 2 seconds to do, like not literally, figuratively 2 seconds, maybe literally a minute. Okay, but go ahead and identify whether it's an exponential growth or decay, and then for 1 and 2 here, I want you to come up with your own examples of exponential growth or decay. Okay, and that's what I'd like you to work on. We'll pause right there, and that's where we'll pick up tomorrow. Okay, we'll finish up there. So go ahead and get to work on those problems, please. Yes, Grace. Sure. Sorry to hear that. Got to stay hydrated.